All right, we're going to be talking about section 8.4, which is linear functions, and some applications of functions. So we're just going to be basically talking about definitions of what functions are and things like that. We're going to be talking about the difference between relations and functions. We're going to be talking about what is meant by domain and range when we're talking about functions and relations. We're going to be talking about graphs of relations and graphs of functions. And we're going to be looking at what function notation is, what a linear function is, and we're going to do an example of how you can model using functions to do real life examples. So what we're going to look at first is, again, when we're talking about functions, we're basically just talking about equations, and we're dealing with, again, this x and y coordinate. In this case, we're talking about x as being the independent variable and y as the dependent variable, meaning it depends on the value of x. And so when we talk about a relation is just any set of points. There's no connection between those sets of points. They don't necessarily form a straight line. It's just a random set of points. So both of these examples that you see here, 1, 2, is one set of ordered pairs, negative 1, 5 is another set, 4, 3, that is a relation. The second example, 1, 5, 9, 0, and 9, 8 is another relation. And again, there's not necessarily any connection between those points. They don't form a line, they don't form a curve, it's just a set of points. So then we can differentiate between relations and functions by saying a function is a relation such that the first component, there's only one value and for each second component. So if you look at the value of f, or the function or the relation f, you have the points 1, 2, negative 1, 5, and 4, 3. So none of the x values or the independent variables repeat. You have 1, negative 1, and 4. So all of the independent variables are different. So this is considered to be a function. Whereas on the second example, you'll notice that you have 9, 0, and then you have 9, 8. So there's a duplication in the x variables. So g is not a function. G is a relation, it's a set of points, but it is not a function. All right, so then when we talk about determining independent and dependent variables, when we're looking at an example, the independent variable is what you're inputting. So depending on what I'm asking you to do, in this example I'm saying find the square root of numbers. So when we take the square root of 81, we end up with 9. So I set up the ordered pair 81, 9. I could add to this relation by saying what's the square root of 16? And the square root of 16 is 4, so I could have another ordered pair in this relation that would be 16, 4. I could do the square root of 4 equals 2, and so I could have another relation in this function that is 4, 2. So the independent variable is the 4 and the 16 and the 81. The dependent variable, the output, is the 4, the 2, and the 9, because again, it depends on what the first value is. So now when we talk about domains and ranges, the domain is always the independent variable and the range is always the dependent variable. Or maybe more simply put, the domain is always the x values, or the first value, and the range is the y values. So let's say, for example, I had a set of ordered pair, and I had the ordered pair, 1, 2, negative 1, 5, and 4, 3. Okay, this is just a relation, and it happens to be a function also. The domain are all the x values, so the domain would be 1, negative 1, and 4. And the range are all the y values, so the range is 2, 5, and 3. Okay, so if we look at that square root problem that we were doing a minute ago, we had a few of the points that we had were 81 and 9, 16 and 4, and 4 and 2. So when they're asking you for the domain, they want all of the possible values for the x's. Well, can I take the square root of any number? Can I take the square root of 80? Yes, it can. It comes out to be 8 point something, but it does come out to be a number, so it does have a unique answer. I could take the square root of 36, and I get 6. So the value of the first number is almost unlimited. What we cannot do is we cannot take the square root of a negative number. The square root of negative 16 is undefined. It is not a real number. So we're restricted. Now here's one more question. Can I take the square root of 0? Yes, the square root of 0 is 0. So the domain can be any number from 0 up. The domain is any positive number. So if we look at our interval notation that we've talked about before, the interval notation shows that 0 is included and it goes to positive infinity. The range, depending on what these numbers are, if I had 1,000,000 in there and I was taking the square root of 1,000,000, I'm going to get a lot bigger numbers for my range. So the range is also from 0 to positive infinity. All right, so when we're talking about graphing relations, again, a relation is just a set of ordered pairs. So we can take any coordinate plane and graph a relation and have a valid relation. So in this situation, we have two examples of relations. This first point right here is the point 1, 2. This point over here is the point -2, 3. This point down here is the point -3, -1. And this point here is the point 0, -2. So our domains, again, are all the x values. So our domain is the 0, 1, -2, and -3. And if you notice how they put these in order, -3, -2, 0, 1. And the range is all the y values. So the range would be the -2, 2, 3, and -1. So in this case, I had a set number of points. I only had 4 points. And so the domains and the ranges are a set of values. You don't have an unlimited or an interval notation. In this example, the domain is, remember what we talked about, the domains are the x values, right? So when you look at the domain, we're looking at the points that are here and here. So the domain is any number between -1 and +1. And the range is any number from -3 to +3. And again, to find the range, I'm looking at this number down here and this number up here. Okay, so when we're looking at domains and ranges, that's what we're looking at. Okay, sorry about that. So now we're looking at this example, and we want the domains and ranges of these numbers. So when you look at the first one, you have to look at, again, look at the x values. And when you're looking at the x values, I could pick any point along here. And there's a very important point to look at here. When you look at this arrow, that's telling you that that blue line goes on forever. So even though the blue line on this graph stops right here, it continues on in one direction forever. So this blue line is actually going on and on in this direction forever, and it's going on and on in this direction forever. So when we look at our x values, we look at this x-axis again. Technically, any number on this x-axis would give me a value that touches the line. So even though, again, I have to remember that it goes on forever. So the domain is negative infinity to positive infinity. And the same thing with the range. When you're looking at the range, you want to look at the y values. And the same thing with the y values. Any number on this green line is going to touch that blue line again. So when we're looking at the range, again, we're going negative infinity to positive infinity. Okay, so a couple more examples. We have, again, looking at our x values, and you've got to remember that this blue line goes on forever up this way and goes on and on forever this way. So it appears that it might stop at some point, but it doesn't. So the domain is everything from negative infinity to positive infinity. And the range, this is where we got to look at our graphs a little bit different. Here's our y. You'll notice that down here, when I draw a line, I'm not touching the graph, and I don't touch the graph until I reach this point right here. So the range starts from this point down here, and everywhere up here, I'm touching the graph. So the range is from -3 to positive infinity. Okay, so what we're going to agree on with the domain is when we're talking about the domain, we have to realize, or we have to agree, that the answer that's going to be obtained is always going to be a real number. That's the only way, that's what we're going to have to look at when we look at domain. So when we're looking at -4, I am able to calculate that out using some higher level math, and I can say that the answer to this problem is 2i, which you may or may not have seen before. But 2i is not real. So when we're looking at a problem and we're deciding whether or not it has a valid answer, we have to decide, is it real or not? And so what we're looking at is we're always looking at the independent variable to see if I substitute in an independent variable, will that give me a real result? So another way of determining whether a function is a graph is to look at the domain, to look at the actual graph. I think I said that wrong. The only way to determine whether a graph is a function is to look at the graph. We can go through and get ordered pairs, but this is an easy way to do it. And what they're telling you to do is to draw a vertical line. And when you draw a vertical line, remember we talked about you can only have one x value. So if I draw a vertical line and I hit my graph in more than one point, then this is going to fail the vertical line test. And so if it fails the vertical line test, then it is not a function. So if the vertical line test passes, oops, yes, then it is a function. Okay, and if the vertical line test fails, then it's not a function. So I'm going to give you a quick example here, and then we'll do two more. Let's say I have a picture that looks like this, and my graph is this green line. So if I draw a vertical line anywhere on the picture, and that's supposed to be vertical, if I touch the graph in two spots, then it has failed the vertical line test. So this is not a function. Okay, one more example that is a function. Okay, let's say I have a problem that looks like this. Similar shape, but turned a different way. Again, draw a vertical line anywhere on the graph, and I touch the graph in one spot. Draw a vertical line anywhere, and you touch it in one spot. And no matter where I draw my vertical line, I'm only touching it in one spot. So this is a function. Okay. All right, so let's look at this one. These are relations, and we're still doing the same thing. So again, if I draw a vertical line anywhere on my graph, on this particular graph, I touch the graph in 3 spots with my vertical line. So this is not a function. Here's another example where it's not a function. Now, even though I can come over here and draw it and touch it in one spot, I have to look at it and sort of be the devil's advocate and try and find a spot where it touches it more than once. So this example is not a function. The second example here, again, I can draw my vertical lines all along here, and no matter where I draw my vertical line, I'm only going to touch the graph once, so this is a function. All right, so basically some different definitions of what is a function and what's not a function. So a function is a relation, and each value of the first component, or each independent variable, has only one second component. In other words, the x values do not repeat. So x do not repeat. Okay? Another way of saying the same thing is that a function is a set of distinct ordered pairs in which the first component is not repeated. Well, that's what I just sort of set up here. And number 3, a function is a rule or correspondence that assigns exactly one range value to each domain value. So all 3 of these are saying the exact same thing. They're just different ways of wording the problem. All right, so the next thing we're going to look at is what we call function notation. And it's just a different way of writing the problems that you're familiar with. And a function notation is read f of x. So for example, if I had this problem down here, I would be saying f of x equals 3x plus 1. F of x is the same idea as saying y. So there is no difference between saying f of x and saying y. The reason that you do see function notation is that as you get into higher level math, not everything is x and y. You know, sometimes we're talking about length and width or some other components. So they want you to get away from thinking of everything as just being x's and y's. All right, so f of x is just another way of saying y equals. But what this does tell us is that I can replace the x and say, what is f of 2? So that means that I want to take this equation that I was given, and everywhere that there's an x, I'm going to be replacing it with a 2 to solve the problem. So what if I said, what is f of negative 2? So I'm going to take this equation, and I'm going to substitute negative 2 in. So I get negative 6 plus 1. So f of negative 2 equals negative 5. So what we've also got here is now we have an ordered pair. 2, 7 is an ordered pair that I can graph for that function. Negative 2, negative 5 is also an ordered pair that I can graph for that function. So this also helps us to get ordered pairs so that we can graph our functions. So this one's a little bit more complicated, so let's see what it's telling us. It wants us to substitute 2 everywhere that there's an x. So we're going to have 2 squared plus 3 times 2 minus 1. So it's 4 plus 6 minus 1. So it's 10 minus 1, which is 9. So f of 2 equals 9. F of 0, we're going to put 0 in everywhere that there's an x. So 0 squared plus 3 times 0 minus 1 equals negative 1. So f of 0 is negative 1. This last one's a little bit more complicated. We're going to take 2x, and we're going to square it, plus 3 times 2x minus 1. So 2x squared is going to be 2 squared times x squared, plus 3 times 2x is 6x minus 1. So this is 4x squared plus 6x minus 1. Now in that last example, since those are different terms, those are not like terms, then we cannot combine anything else together, and that's our final answer. All right, so another way, we've talked about linear equations, and a linear equation, remember what we did earlier, was y equals mx plus b, where m is your slope and b is your y-intercept. So that same problem can be rewritten as function notation. And so if I rewrite it as f of x instead of y, then I just call it a linear function instead of a linear equation. So here I want you to graph each linear function. So I'm going to do this the same way that I did before. M is -2/1 and B is 1. So if I graph it on my graph, I'm going to graph the B value. So I'm going to graph at +1 and put a dot. And then I'm going to use my slope, and I'm going to go down to 1, 2, and I'm going to go to the right one. So there's my new point. And remember what I did again. Whoops. Let's go back to that. Okay, don't know what happened. All right, so we went down 2/1. We have our other point here. So again, what we did is we used our slope and we went down 2, so -2, and then we went +1. And so now I can connect those 2 points together, and there's my linear function. Now remember, this is the same thing as saying y equals 2. So when I graph this one, I want all the values where y equals 2. So I'm going to end up with that horizontal line at y equals 2. And both of these are linear functions. If we do our vertical line test, if I go through and do my vertical line, I'm only hitting the graph at 1 point each. Where over here, if I do my vertical line, I'm only hitting the graph 1 time. So these are functions. It's just because it's called a linear function, we know they form straight lines. All right, so here's our applications of this. So here's our first one. We're going to do 2 of these. A company produces DVDs for a live concert. The company pays $200 in advertising, so that's a flat fee that they have to pay. Each DVD costs $12 to make, and they charge $20. So they're making like $8 per disc. So first of all, I want you to express the cost as a function of x to represent the number of DVDs produced. So the cost is going to be C of x, okay, equals, it costs me $12 per DVD to produce them. So 12 times x, plus I've got that flat $200 advertising fee that I have to pay every single time. Okay, now the revenue means how much money do I make? The revenue is $20 per disc. So 20x is my revenue. So when will I break even? I'll break even when the cost that I'm spending equals the cost that or the price that I'm paying, or price that I'm making. So I'm going to break even when 20x equals 12x plus 200. That's when I'm going to break even. Okay, so let's look at this. That's all this is telling us here. So the fixed cost is $200, and each DVD costs $12 to produce. So the cost in terms of x is C sub x equals 12x plus 200. So this is function notation. We talked about that before. That is function notation. Even though I'm not using f of x, this is what I mean by function notation. Sometimes makes it a little bit clearer what we're dealing with. Part B, we talked about, it costs $20 to buy each DVD, and so $20 per DVD would be 20x. And then our last step, how much will it cost, or how many DVDs do we have to sell to break even? We're going to take this 12x plus 200 equals 20x, and we're going to solve it. So we're going to subtract 12x from both sides. That's where we get our 8x, and then we're going to divide both sides by 8. So 200 divided by 8 is 25. So I have to produce 25 DVDs before I'll break even. So a lot of times you'll have a company that might say, you know, we will make these CDs for you, but you have to guarantee us that you're going to sell at least 25 of them, or you have to pay for at least 25. And that's because that's how much it costs the company just to break even. Okay, so here's another one. Bart runs a copying service in his home. He paid $3,500 for the copier and a lifetime service contract. Each sheet of paper that he uses costs a penny, and he gets paid 5 cents per copy that he makes. So express the cost. Now, if you can imagine this, he's got to make at least $3,500 in order to break even. So that's a lot of copies that he has to be able to make it just to break even. So the cost is going to be 1 cent per copy plus that $3,500 copier fee. The revenue is going to be 5 cents per copy, and the break even is when those two numbers are equal to each other. So that's what we're looking at again on the next page. The cost is $3,500. The variable cost is 1 penny per piece of paper. So X represents the number of paper, or the number of copies. So 1 cent per copy plus the $3,500 is his cost. A copy earns 5 cents. So 5 cents per copy is his revenue, how much money he's making. So I'm going to break even when the amount it costs me to make the copy equals the amount that I sell them for. So again, we're going to subtract 0.01 from both sides, and we get a 0.04. We're going to divide both sides by 0.04, and I find out I have 87,500. So in order for me to break even, I need to make at least 87,500 copies. So that's not necessarily unrealistic when you're looking at a large company. All right, I hope this helps. Keep in touch with me. Let me know if you're having any problems, and have a great week.